Okay, let's begin. So we are studying number systems. Yesterday we saw what are natural numbers, like the set of natural numbers. Its existence is guaranteed by the axiom of infinity. And well, this was also a question around 100 years ago. Yeah, people wanted to formalize mathematics. And well, while preparing for this class, I just came across this video. There is a 379 page long proof of 1 plus 1 is equal to 2. Yeah, I mean, what if you are finding my yesterday's lecture ridiculous, then I don't know, you will die laughing when you see this. Okay, so why are these things important? Because human beings want to formalize things. They want to reason about things without really knowing what things are. Yeah, things are black boxes and you want to reason, and therefore logic is the most appropriate language for talking about things. So we saw yesterday what is principle of recursion. Yeah, it's a theorem which allows you to define functions on the entirety of omega, which is the set of natural numbers. And we also saw the distinction between omega and n. Yeah, n with one extra line. So don't forget that extra line. Otherwise, it's just some capital N English language letter. It doesn't mean anything. Okay, so let us move ahead, and we want to construct. Yeah, I mean, the zeroth stage was, of course, natural numbers. Zeroth stage is natural numbers. So the notations are, I mean, n, then somebody asked me yesterday what this blank was. So this blank is just a placeholder for an argument. So blank plus the shift operator, then the addition as an operation from n cross n to n, and multiplication as an operation from n cross n to n. Yes, and we also saw exponentiation. Now we want to extend it in stage 1 to integers. So yesterday I pointed out that in natural numbers, subtraction cannot be done, or rather subtraction is only partially defined. If you want to subtract 2 from 3, you can do it, but you cannot subtract 3 from 2. Yeah, so it's a restricted operation. So we want to allow ourselves to have negative integers and subtraction also. So any ideas on how to do this, achieve this from natural numbers? What were you told in school? How do you motivate natural numbers? Or you don't remember, you are too young. Yeah, it has been an integral part of your understanding that natural numbers exist, imaginary numbers exist. Yes, somebody?
Like counting numbers.
Counting numbers. So what is minus 1? Can you count minus 1?
No, I was talking about natural numbers.
Yeah, that's okay. But for integers, what is the motivation? Okay, you are thinking actually, that's good.
Left of numbers line, then we get negative numbers. And
We get to?
if we go left,
If we go left of the number line, yes.
then we get negative numbers.
When you are answering this, then you are assuming that you know what the number line is.
Yes, in school.
Yes, number line is, yeah, we don't really know what the number line is. Yeah, you know we are facing problems and we are asking questions for everything. Yes?
So profit loss in business.
Proper?
Profit loss.
Profit loss in business. Okay, yeah, that's a good motivation. Yeah, we want to be able to subtract things. Yeah, and therefore we create these new symbols. Yeah, minus 1 is simply a new symbol which when added to 1 will give us 0. However, now that we are learning set theory, we should formalize this process, and so consider n cross n. we are going to cheat. Okay? We only know how to add, and we are going to use addition to describe subtraction. Okay. So consider a n cross n. Yeah, this is the collection of natural numbers. Ordered pairs of natural numbers. Okay. And define a relation tilde on this set. Well, what is this tilde relation? So we say for a comma b in n cross n, well, a comma b and c comma d, these are two ordered pairs. Say a comma b is related to c comma d if a plus d is equal to b plus c. So let us assume that we have proven that addition is commutative and associative and everything using mathematical induction. Yeah, hopefully all of you know mathematical induction. Yes. So now observe this, a plus ab is related to cd if a plus d is equal to b plus c. So in particular, a minus b is equal to c minus d. So this pair is supposed to represent the difference between those two numbers. Yeah, a comma b is a minus b. It is meant to represent that. But as we know, 1 comma 2, which is minus 1, is also same as 2 comma 3. So therefore we should have an equivalence class of all such things. So I am just going to write this clearly, or prove that tilde is an equivalence relation. Yeah, hopefully you can do that without any problems. Reflexivity, symmetry and transitivity. Okay, so tilde is an equivalence relation, and then define Z to be equal to the set of equivalence classes of ordered pairs of natural numbers with respect to this relation. Yeah? So these are precisely the integers. Yes, you have something? Say. Sorry?
What we define as set?
It is the set of equivalence classes. Oh, you want more explanation? I can write it. Yeah. So that is also equal to. So I take the AB and the tilde equivalence class such that A comma B is like this. Well, do you want some primer on this? So suppose, yeah, I mean, I'm going to write it in a different color. If E is an equivalence relation on a set A, then for A in A, this class, yeah, maybe I can use this also, yeah, to make it more precise. I can write square brackets over here. This is the collection of all those B's in A such that A is related to B, yeah, and A modulo E is defined to be the collection of all such equivalence classes of elements of A. These equivalence classes are precisely, they will form a partition of your set. Yeah, all of you know this? Yesterday I asked you for this specific reason if you know this. Yeah, so just make sure you write these square brackets around these ordered pairs over here. Okay.
What is AEB?
What is AEB? It is a binary relation. A is related to B via E. Yeah, just like we wrote this, you never objected to this. A comma B is related to C comma D. When tilde was replaced with E, then it means the same thing. Yeah, it's a relation. So all of you are okay with this definition of integers? Yeah, we started with pairs of natural numbers and we defined their difference. The intended meaning is the difference. And this will be our new integer. What will be 0 in this case? 0, 0 or 1, 1 or 2, 2, anything. All of them will be equivalent. So that will be our 0. Yeah. So let us write that down. So in Z, 0 is the class of A comma A. Then minus, yeah, this is precisely what we wanted to do. Minus of the equivalence class of AB is defined to be then what is the sum? What is the sum? Coordinate wise sum, correct. A plus C, B plus D. What is product? You multiply A minus B and C minus D. What do you get? In the positive part, you have AC plus BD, very good. And in the negative part, AD plus BC. So it is, these are all the equivalence classes. Yeah, exponentiation I am not going to do. You do it on your own. Because the exponentiation is only defined for natural powers, not minus powers. Yeah, the values won't lie here. So let's just be content with this definition. So in algebra you will study rings. Yeah, so we have described the ring structure here. We have 0. We also have 1. 1 is the class of 1, 0. It is then we have subtraction, we have addition, and we have multiplication. So this is the ring structure of integers. Whereas natural numbers are called semi-rings. Yeah, they have only half of the ring structure. They don't have subtraction, they don't have division, yeah, so only half of it. Okay, so now that we have defined integers, we can also go ahead and define rationals. So how are rational numbers defined? Now can you use the same idea? Yes?
A is equals to BC, that relation.
Yes?
Like we can define a relation from
Relation from, yes. Relation from or relation on?
on
On?
Z cross Z.
On Z cross Z. Do we want Z cross Z entirely? What is the intended interpretation of a pair? P by Q. So can we divide by every integer? No. Right. So you have to remove. Yes. We have to remove 0 and then AD equal to BC. And maybe we can also say that the denominator just happens to be positive. We don't really need negative denominators because minus P by Q is same as P by minus Q. So, yeah, so define double tilde on, yeah, I am just going to define this on Z cross Z plus. Yeah, Z plus is all positive integers as A comma B double related to C comma D if AD is equal to BC. Yeah, this is our multiplication, and then you can write down the rest of the things. Yeah, I don't want to do it. You can add, you can subtract, you can have 0, you have 1, you have multiplication, you have division. Everything can be done, right? So
आपने वो assume नहीं किया जब आपने बोला कि minus वो कट जाएगा.
English.
So then haven't you assumed that the minus from the denominator is same as the minus in the denominator, numerator?
I did not assume.
So how will that?
We can, okay, if you wish, you can also do it with Z cross Z minus 0 and do the same thing. It's not going to change the answer. The equivalence classes, the set of equivalence classes will still be in bijection. Yeah, I mean, I'm just going to write this, yeah. Can also use Z cross Z minus 0 and define the same equivalence relation, everything will work out properly. Okay, so these are your rational numbers. Okay, what comes after rational numbers? Irrationals. No, I mean irrationals have a negative definition, yeah. Whenever you use some adjective like ir, yeah, that means not rationals. But not rationals where? Real numbers. So how do you define real numbers?
Using LUB property.
Using
The density, like the LUB.
density. Okay, yeah, density property, yes. Can we do it slightly differently maybe? Yeah, that's Cauchy completion is one of the ways. Yeah, all of you know what is a Cauchy sequence? Yes, Cauchy sequences of real numbers can be defined, and Cauchy sequences are convergent in real numbers, and so you can formalize that part, or you can do it via density, like completion. Yeah, just completion, order theoretic completion of rational numbers. That can also be done. Or, I mean, yeah, so one more thing you can define on rational numbers and integers is what is the order, right? You can also compare two rational numbers to integers, yes? Okay. So, what other way of defining or using real numbers do you know? How do you express a real number? Decimal expansions, very good. So, can we formalize decimal expansions?
Like there are 3 kinds of decimal expansion of a number, like terminating, non-terminating.
Terminating, non-terminating. I mean, we can also say that everything is non-terminating. Yeah, if it is terminating, then you just pad it with zeros eventually. So, real numbers, yeah. For real numbers, what do we need? Every real number has some integer part and then some decimal expansion part, right? You write n dot a1, a2, a3 and dot dot dot. So what is this a1, a2, a3 dot dot dot? Decimal expansion. So that means you are choosing a function from what? From naturals, yeah, not from 0 to 9. 0 to 9 is the codomain, and from natural numbers to 0 to 9. Okay, so this part is a function from natural numbers. I mean, okay, maybe for natural numbers I should, okay, it's not rubbing. I will use a0, a1, a2 and dot dot dot, a function from omega to 9. Yeah, which in our language is precisely the set 10. Right? Okay, so this is a function and this is one element from integers. N is, yeah, n simply belongs to integers. So now what do we know? So we have to take z cross functions from omega to 10. Okay. Are all real numbers mentioned here? Are there more real numbers than this collection, or are there less real numbers than this collection?
Definitely not less.
Definitely not less, because every real number does have a decimal expansion. But can the same real number have more than one decimal expansion? Yes. What are such numbers?
0.9 bar.
0.9 bar, yes, correct. So we have to quotient out this by another equivalence relation. Yeah, so this is our set of real numbers where, okay, how do you describe anything? Yeah, so n comma a0, a1, a2 up to an and then 99999, 99999, okay. So this is equivalent to, what do you do? I mean, you have to add 1. Yeah, let's not try to make this precise, but n dot a0, a1 up to an plus 0 dot 0, 0, 1. Yeah, where this 1 is at the nth position, this is at the 0th position, and so on. So you add this, and then the rest of, oh, I mean, I should have written, perhaps I should erase this part. I should say something about zeros, yeah. And plus 0.00 up to 1. Yeah, this is also 0, this is at the nth position, and whatever number you obtain here. So there is also one equivalence relation by which we have to quotient out, and then the rest will be taken care of.
So you should add 0 with the second one also.
Yes, thank you. Yeah, whatever this addition means, addition is always pointwise, but we have to also carry 1 if necessary.
But an will not be 9, right? Like assuming that. Because we are assuming that an is the last non-9.
Okay, good observation. So where and an is not equal to 9, so we can change that, but I'm still not going to do it. If it's a negative number, then what do you do? Yeah, so let's keep it as it is, but yes, his understanding is correct. An is not equal to 9 because we started saying 999 after nth stage. Right, so this is the only equivalence relation. Yeah, of course we know that 0.99999 is same as 1. Yeah, so that's precisely what we have written down, and these are real numbers. And so far so good, because we have never used anything more than what we know. We have only used sets, and natural numbers to begin with, and we have used equivalence relations, which are set theoretic constructs. Right? So again, addition of real numbers, etc. My purpose is not to teach you basic high school mathematics again, but just to make you think about how you can arrive at something like this formally. Okay, you can compare real numbers, you can add, you can subtract, you can multiply, you can divide by a non-zero real number. So it's a field. Yeah, you are also learning linear algebra. So this is real numbers form a field. So do rational numbers. They in fact form, both of them form ordered fields. Yeah, there is also an order relation which behaves nicely with respect to the algebra structure. Right? So this is our end of story for number systems. You know how to construct complex numbers. Yeah, complex numbers are also pairs of real numbers. Yeah, ordered pairs of real numbers. So, and you know how to add and subtract. So everything just works nicely. And now we can start asking some good questions. So for example, what is the size of integers? Can you list all integers? Listing means finding out the first one, then second one, then third one, and so on. Can you list all the integers? Yes or no? Not sure? Okay, now I should add a page over here. Yes, okay. So, well, now when I am talking about integers, I will use positive and negative symbols. Can we list all integers? I can start at 0, then I can say 1, minus 1, 2, minus 2, and dot dot dot. Now by principle of recursion, we can actually complete this sequence, and that will define a bijection between omega and natural number and integers. Yeah. So therefore, yes, and this is the answer. Use recursion. To define this function. So therefore, what we have concluded is that omega is equinumerous with integers. What can you say about rational numbers? Can you list all rational numbers? Yes? How?
It is a relation between it can be written as p by q, right? So
It can be written as p by q, correct?
so like similarly we did for integers, we can do it for rational numbers.
What is the meaning of similar? How?
Like we established a bijection, right?
Uh-huh.
So it is like 1 and minus 1.
Huh?
In that case, if for rationals we can define it as like some x1 by x2 and so on, we can list all those.
Yeah, but can you try to formalize your argument? We want to, so look at what are rationals. Rationals are defined on z cross z plus or z cross z minus 0. Now, even if we can show that all the elements of z cross z can be listed, then we are done. Yeah? Because then these are quotients, so they will be countable. Well, that will only show they are countable. It doesn't show that they are countably infinite. Understood? For proving countability, what do you need to show? Okay, so let me write this down. A set A is countable if there exists an injection or equivalently this is same thing, or there is a surjection from omega to A. Yeah, take this as a homework problem. Yeah, these two are equivalent conditions, and the set is countably infinite if there exists a bijection H from A to omega. Now, what method do we have of proving bijections, like existence of bijections? Cantor-Schroeder-Bernstein theorem, right? CSB theorem. So clearly, natural numbers embeds inside rational numbers. Correct? Rationals are denoted with Q, symbol Q. So you only need to show that there also exists, right? And actually, I mean, maybe I should write this down. So Z cross Z minus 0, if that's the notation we are using, then from here to here there is a surjection. Yeah, that's how we constructed rational numbers. So we should be able to, so it is enough to prove that Z cross Z is, I mean Z cross Z or Z cross Z minus 0 equivalently is countably infinite. So we'll simply prove this. Yes?
So what is the symbol omega to Q?
That is the inclusion symbol. So injective functions are denoted with an arrow with a tail, whereas inclusion is denoted, it's a subset. Yeah, omega can be identified with a subset of rational numbers. Yeah, so this is a symbol for inclusion. Okay, so actually instead of proving this particular thing that Z cross Z is countably infinite, we will prove that product of two countable sets is countable. Okay. So if A and B are countable or are respectively countably infinite, then so is A cross B. Okay, so product of two countable sets is countable if one of them happens to be, like if both are non-empty and one of them is countably infinite, then the result will also be countably infinite. Okay, how do we do this? Well, in this case, we always have bijections. We have bijections f from A to omega and g from B to omega. So basically, so what is a bijection? Bijection is simply renaming. Yeah, I take the class of the students and I replace them with their roll numbers. It's one-to-one correspondence. Yeah, it's renaming. So therefore, by default, it would be, I'm just doing it for, countably infinite, but countable argument is also similar. So it is enough to do it for omega cross omega. And I am not going to give you a formal proof or anything. You can convert this diagram into a sequence. So let us list all elements of omega cross omega as follows. So what the first element is 0 comma 0, then 0 comma 1, 0 comma 2 and dot dot dot. Then here I am writing 1 comma 0, 1 comma 1, 1 comma 2 dot dot dot, 2 comma 0, 2 comma 1, 2 comma 2, and now this is just child's play. I will take color green and I will start from here, this zigzag. This zigzag actually defines a list of all the elements. Every element lies on some diagonal, so it will be covered at some point. Yeah, converting it into a bijection is not hard. Explicit bijection. Yeah, if you wish, you can invest your time and find out the formula for this bijection. But it's not necessary, is it? You understand, listing is saying that this is my first element, second element, third element, and so on. Okay, so product of two countable sets is countable. You can use the same argument. Yeah, I mean, I just did it for infinity, but you don't need to. What about union? Union of two countably infinite sets or two countable sets. Will that still be countable?
Yes.
Yeah, how?
Odd and even numbers. Like if they are disjoint.
Yes, yes. So if those two sets are disjoint, or we can assume they are disjoint by default, yeah, then disjoint unions of countably infinite sets will again be countably infinite. It is same thing that we did for integers also, right? All the odd integers were positive and the even integers were non-negative, right? It was 0, 1, minus 1, 2, minus 2 and so on. So for 2 you can use this idea. What about finitely many countably infinite sets?
Divide like depending on n.
Yes, so we can use the congruence classes, congruence classes of natural numbers like modulo n. If there are n many countably infinite sets, well, I will just note it down. Yeah, for if a1, a2, an are countably infinite or countable, yeah, you can write down the other version, then so is the disjoint union of AI. Okay. Yeah, use bijections of AI or AJ with the congruence class m n plus j minus 1, yeah, such that m belongs to integers. I can also do it with integers. Yeah, integers we have already proven to be countably infinite. So I can establish this. Yes. What is the congruence class? This is precisely the congruence class. So the congruence class modulo n of 0 is 0, n, 2n, minus n, minus 2n, all of them. Then congruence class of 1 is 1, n plus 1, 2n plus 1, and so on. Yeah, so these are the congruence classes. Yeah, this is modular arithmetic. Okay, so you can do this. So use bijections of this, and then the disjoint union will be precisely integers, and integers are in bijection with natural numbers, so everything works properly. Any questions? This one. So this is precisely, I mean, I can list all the elements. This is j minus 1, then n plus j minus 1, then n plus 2n plus j minus 1, and dot dot dot. Here, here it is minus n plus j minus 1, minus 2n plus j minus 1, and dot dot dot. So this set.
Like, how are we using this set?
How are we using this? Okay, this set is infinite. Yes. So it is countably infinite in particular. So Aj is countably infinite. So therefore there exists a bijection between Aj and omega. Yeah, by definition there exists a bijection with omega. Omega is in bijection with integers, and integers are in bijection with this. Yeah, so by transitivity of numerosity relation, yeah, we can get this. Okay, maybe I should write it down if you have questions. So Aj is equinumerous with omega, yeah, by definition. Then omega is equinumerous with z, we have shown, and z is equinumerous with the part below it. That's clear. Yeah, that's just via m. Any questions? Okay, so perhaps to end this session, we should push our boundaries and ask, can we make this result better?
Yes, like with n cross n, you can identify with n cross n with countably infinite units.
Yes, so countably infinite sets, but a countably infinite family of countably infinite sets. If we are given that, then is the union of this family again countably infinite? Yes? Anybody else? Yes or no? Maybe I should write down the question. Yeah. Suppose A0, A1 and dot 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 is a sequence of countably infinite sets. Then union of ai, I in omega, is countably infinite. Yes? So two people have said yes so far. What's your argument?
You can identify it with omega cross omega, like each AI.
Each ai,
Like
identify each ai with
No,
omega
no,
cross
like
omega.
all of them together with omega cross omega. Like take like a row in that.
So there exists a function perhaps, yeah?
Yeah.
So they are saying yes. So choose a function f0, fi from ai to omega. Yeah, I mean choose a bijective function for each I. Then list all the elements, right? We can list all the elements. What will be the first element? So the first row would be f0 inverse of 0, that would be the first element. Then f0 inverse of 1, then f0 inverse of 2, and dot dot dot. In the second row we will write f1 inverse of 0, f1 inverse of 1, f1 inverse of 2, and dot dot dot. And then what argument will you use? The zigzag argument. However, yeah, there is a catch. This is not yet done. There is something that I have written that warrants question. So what did we say in the first line? Choose a function fi. Yeah, choosing one function is not a problem at all. But choosing infinitely many functions at the same time is a problem. And perhaps you can smell what's coming. Axiom of choice. We only need a specific version of that, and that's axiom of countable choice. Yeah. So this is only possible. So the answer is yes, assuming axiom of countable choice. Yeah, so AC the omega, it is the axiom of countable choice. Well, literally, axiom of countable choice just says that you can make countably infinitely many choices at the same time. Well, you might ask why, but we are going to do an entire lecture on axiom of choice and its equivalents. Okay, so this is for some other time. We don't want to do it just yet. Yeah, so the proof of this works like this. Result is true only if you assume axiom of choice or a weaker version of that. If you do not assume axiom of choice, then the result is not true. It seems something quite obvious, yeah? This argument always works, but that argument involves something which is very strong. And it is not just strong, like its strength is not the problem. Yeah? The problem with axiom of choice is that it is a statement which can neither be proven nor be disproven. Okay, that's the beauty of this statement. So it can be shown that axiom of choice can neither be proven nor be disproven. Okay, it takes time to understand and appreciate this particular statement. Yeah, therefore it's quite a controversial statement, but we'll talk more about it. So Paul Cohen won a Fields Medal for showing this. Yeah, that there are statements which can neither be proven nor be disproven. They are independent of all the other axioms. Okay, we'll talk about it in later future because you need to be more mathematically matured before that. Okay, so we'll stop here for today.